Hello, my name is Xingyu, and today I'll be talking about the optimal ordering and the optimal stopping problem. And my co-authors are Shipra Agrawal and Sethuraman. So first, what is the optimal stopping problem? So imagine this situation. You are HR for a company and you have N potential candidates for hire, but you can only hire one of them. You don't know how good any of the candidates are in the beginning, so therefore you need to interview a candidate to discover how good they are. And after you interview a candidate, you discover the quality of this candidate, and this quality is drawn from a distribution that is known to you. And furthermore, for different candidates, they have different distributions. And in this context, you can think of these distributions as information you gather from the resumes that you have for each candidate. And you as HR, your goal is to maximize the expected quality of the candidate that you hire. Now, there are more rules to this. First, you have to sequentially interview the candidates. And after you interview a candidate, you know how good they are. And now you need to make a decision whether to hire this person or not. If you choose to hire him, then you get the reward. So here the reward is the quality of the candidate, and then the hiring ends. If you choose not to hire him, you can potentially interview other candidates, but you can't in the future go back and try to hire this person. Now, if the order of candidates is fixed, so therefore suppose there are 3 candidates, candidate 1, candidate 2, candidate 3, and if they have to come in this order, then it's actually optimal to use DP to find the stopping criteria. So the stopping criteria here is the decision whether to hire the candidate or not. So for example, in this 3 candidate case, after you interview the first candidate, if the quality of this candidate is higher than what you would expect from the other 2 candidates, then you would accept this candidate. Otherwise, you would reject and then interview candidate 2. And when you interview candidate 2, if the quality of this candidate is higher than the expected quality of candidate 3, you accept candidate 2. Otherwise, you reject. And if you reject candidate 2, then you have to accept candidate 3. So that's the case for a fixed ordering. So for a fixed ordering, finding the stopping criteria is easy using DP. Now, the main focus of our work is if you have to choose the ordering of the candidates as well as the stopping criteria, what is the best ordering you have to choose in order to maximize the expected reward at the stopping time? So you can imagine that in many real-world settings, including hiring candidates, you as the decision maker, you have the control over the ordering. So as HR, you can choose which candidate to bring in first and which to bring in second. So in many real-world settings, it's realistic that you can choose the ordering of the variables that you probe. Now here I'm going to talk about a simple example that shows that ordering can make a huge difference. So here we have 2 variables, x1 and x2. And x1 can take on values 0, 1 with probability 1 minus a and a. And x2 always takes on value a with probability 1. And in this case, there are only 2 orderings. Either we interview x1 first or x2 first. In the case, in the ordering x2, x1, so we interview x2 first and then x1, this happens to be the worst order. And to see this, after I interview x2, we know that it gets a value of a. If we hire x2, then we get a as a reward. But if we reject x2, then the expected quality of x1 is going to be a as well. So basically, in this ordering, we always get an expected reward of a. In the other ordering, x1, x2, this is the best ordering. So in this ordering, when we first interview x1, if 1 appears, then we accept with probability a. And when 0 appears, we reject, and then we just accept x2. And x2 has expectation a. So in this case, we get an expected reward of 2a. And in the random ordering case, when both orderings happen with 1/2 probability, we get the expected reward of 3/2 A. And finally, for the offline, so this is the expected maximum of both random variables. The expectation is also 2A. And so in fact, here we see that the best ordering coincides with the offline expected value and is twice as large as the worst ordering and is still substantially larger than the random ordering. So if we can get the best ordering, sometimes we can get a much higher expected reward. So now some history about this problem. So this problem was studied in the 80s. And in those papers, they give some specific positive results. So they find optimal orderings for specific 2-point distributions and also the exponential distributions and some other results. A field that's related to our work is the profit inequalities. So profit inequalities, they provide an approximation to our ordering problem. So the profit inequalities, they compare the expected reward of the online algorithm against the expected offline algorithm. So sorry, the expected offline reward, which is just the expected maximum of all the random variables. So here in the adversarial setting, so when the ordering is adversarial, there's a type 2 approximation. And for random ordering, the current best is roughly 1.5. And for 2-point distributions, it reduces to, it becomes 1.366. And finally, there is a p-TOS for approximating the expected reward under the optimal ordering. And this was recent in 2018. So what are our contributions? First, our main goal is we want to find the optimal ordering of distributions to maximize the expected value at the stopping time. And we have 4 main contributions. The first is we have a hardness result that holds for 3-point distributions. So distributions with support size 3. And in fact, these are very specific 3-point distributions. So here the left and right endpoints are the same and the middle point is different. In addition, we show that in this case, there is a f-p-TOS, which is, so this improves on the p-TOS result from before. And this holds when the left endpoint can be different. So here only the right endpoint needs to be the same. Finally, we have a optimal ordering for 2-point distributions, and we have a 1.25 profit inequality that holds for 2-point distributions. So first we'll talk about the optimal algorithm for 2-point distributions. So here, each random variable has support on only 2 points. And we have a result that is quadratic time for finding the optimal ordering for 2-point distributions. So first we want to make some remarks. For a fixed ordering, a dynamic program can be used to find the optimal stopping policy. And here, actually, the optimal stopping policy reduces to a thresholding policy. So what does that mean? That means that for each random variable, we assign a threshold. So if we assign a threshold t to random variable x, it means that after I interview candidate x, if his quality is higher than the threshold t, then we accept him. Otherwise, we reject him. And in fact, using DP, the optimal thresholds are the DP thresholds, and the DP threshold is the expected reward from all the remaining variables left in the ordering. So we accept if the reward is higher than the DP threshold, otherwise we reject. And also, if we reach the last variable, then we always just accept that variable. Now here's a main observation that we use to get the optimal algorithm for 2-point. The observation is this: there exists an optimal ordering such that no variable apart from the last variable is always accepted when probed. So what does that mean? If there's a variable that you would always accept, that means that you intend to accept that variable and to finish the game. But you can imagine that there can be another policy where you examine the other variables. So the worst case is you examine the other variables and you reject all of them. And then finally, you accept the variable that you meant to accept always. So basically, there exists an optimal ordering such that you never probe a variable that you will always intend to accept. And we use this observation to get this property called the left endpoint property. So this property holds in an optimal ordering for all the variables except for the last variable. And what this property says is that the DP threshold for every variable is larger than the left endpoint. And so this holds for 2-point distributions. And what this means is that apart from the last variable, when you probe the other variables, if the left endpoint shows up, you would always reject that variable. And so under this left endpoint property, suppose we fix the last variable, then for the remaining variables, we can prove that for those remaining variables, we would always order them in a decreasing right endpoint fashion. So here's an example. On the left endpoint, we have 4 unordered variables. So we have x1 on the top, and then x2, x3, x4. So a potential optimal ordering is the one on the right. So here we fix some variable to be last. So here x1 is last. And we have the remaining variables x2, x3, and x4, and we order them in decreasing right endpoint. So here we examine x3 first because that's the highest right endpoint, and then x4, and then x2, and then finally we examine x1. In reality, we don't know which variable is going to be the last one. So in our algorithm, we would have to loop through all the variables and try to place them as the last one, and then order the remaining by decreasing right endpoint. So this is what gives the O of n squared runtime. So next we have a hardness result. So as said before, if the ordering is fixed, it is easy to find the optimal thresholds using DP. So conversely, if the thresholds are fixed for each variable beforehand, it's also easy to find the optimal ordering. So if the thresholds are fixed, then each variable actually reduces to a 2-point distribution. So it has support on 2 points. Basically here it's 0 and this conditional expectation. So this is the expected value of x given that x is greater than the threshold with probabilities probability x less than t and probability x greater than or equal to t. And because we know how to order 2-point distributions, we can actually order these random variables. And here, because all the left endpoints are the same, they're at 0, the order is just by decreasing right endpoint of this new 2-point distribution, which here is it's in decreasing conditional expectation. So basically, we show that instead of trying to find the optimal ordering, we can try to find the optimal thresholds instead. And we show that finding the optimal thresholds is a hard problem. And we do this by a reduction from subset product. And so here we consider 3-point distributions. So they have the same left point and right point, but they have different middle points. And when we decide on a threshold for each random variable, it effectively divides them into 2 sets. So here, the set S are the variables that are accepted only when the variable 1 is realized. And the set T are the variables accepted when either M, the middle point, or the right point is realized. And we can show that in an optimal ordering, we always examine the variables in S before T. And also the variables in T are ordered by decreasing conditional expectation. And this is from our 2-point result. And so we show that subset product can be reduced to actually deciding whether to place the variables xi into S or T. So it reduces to this partitioning problem. And in fact, in the details of the proof, it requires carefully setting the values for mi, pi, and qi. And next we have a f-pitas. So as remarked before, there is a pitas. And here we give a FP task for 3-point distributions with the same right point. Again, we use the notation from the previous slide. So S are the variables where 1 is realized, and T is the variables where either the middle point or the right point is realized. And at iteration I, we maintain a polynomial size collection of partitions for the variables x1 to xi minus 1. And then for each partition, we replace that partition with 2 partitions. So basically, we try to place xi into S, and we try to place xi into T. So here, with this step, we double the number of partitions. And then in the next step, we try to reduce the number of partitions. And here, if we have 2 partitions where Tj and Tj prime are close, so close here means that the expected reward of all the variables in Tj is close to the expected reward of all the variables in Tj prime, then we remove one of them. And in fact, the one we remove is we look at the expected value of Sj, the expected value of Sj prime, and we remove the smaller one. Finally, we have a result on 2-point profit inequality. So as a reminder, the profit inequality is a constant bound on the ratio of the offline reward, which is the offline expected maximum, with the expected reward of the online algorithm. So in the worst case, there is a 2-point profit inequality, that's 2. And this can be improved to 1.25. So we give an algorithm for doing this, but we don't have time to talk about it. And in fact, this is a tight bound. So here's an example of tightness. Here we have x1 and x2. And you can show that in this example, the expected offline is roughly 5/4. And for both orderings x1, x2, or x2, x1, the expected reward is going to be 1. So here the ratio is 1.25. So in conclusion, we give a near resolution of the question of the optimal ordering in finite support case. For 2-point distributions, we give a quadratic time algorithm. We also give a hardness result for specific 3-point distributions. Then we give a FP task for those distributions. And finally, we give a tight 1.25 profit inequality for 2-point distributions. And for further directions, so here are 2 potential further directions. Is there a way to extend this profit inequality? And also, is there a way to extend the FP task? So here we have FP task for these 3-point distributions. Is there a way to extend that or show that it's not possible? All right, thanks a lot.